Hello guys, and welcome to VIT Mathematical Association's ongoing series on MATLAB. In this module, we'll discuss a new and interesting topic called Lagrange multiplier. First of all, we need to understand what Lagrange multiplier is. Lagrange multiplier is kind of a method to solve maxima and minima for multi-variable functions. Now, we can solve maximum minima for multivariable functions in a few ways, but generally, Lagrange multiplier is preferred when there is such a function that there is a constraint. Basically, let's say that we have to maximize the surface area of a cube, and its maximum volume cannot go over a limit. Let's say 162. So let's say x, y, and z are the length, breadth, and height of the cube. Then xyz minus 162 will be the constraint, like that. So it's a very specialized thing, but it's pretty useful further in your engineering studies. Now, uh, yeah, basically, when we write a Lagrange multiplier, we write it as a f of x, capital F of x, which is defined as a small f of x plus lambda times g of x comma y. Now, small f of x is the function that we are uh, small f of x is the function that we are optimizing, while g of x comma y is the constraint or the limit which the function has put on the greater function. Now we write it all together as capital F x of y equal to small f x comma y plus lambda times g x comma y, and yeah, basically what I said. Now there are just two steps to solve this. First, we have to partially differentiate to obtain fx and fy, which is dou f upon dou x upon dou f and dou f upon dou y. This gives us the this gives us the two fx and fy. Now we'll get a relation between f of x between fx, fy, lambda, and gx of y from this. Now we solve all of these constraints with respect to lambda, x, and y. We obtain some values of x and y, and the special thing about Lagrange multiplier is that the values of x and y we obtain, we do not know whether they are minima or maxima. It entirely depends on the question. Now, without further ado, I think we should just move on to the board. Now, principally, what we should do is CLC and clear all or clear, even if there's nothing there, just put it there. Now, sims x, y, l. I'll explain what this L is. Basically, sims means symbolic variable, right? So sims of x means a symbolic variable x has been assigned whose value is not known. Sims of y means a symbolic variable y is assigned whose value is not known, and L is the Lagrange multiplier, or basically this lambda. Now, let us take an example problem. Let's say that there is a function like, let's say that the function that we have to optimize is x square plus y square, and the limit is x plus y minus 10. Okay, so we define a function f of x comma y, small f of x comma y equal to x square plus y square. We define the constraint, which in this case is g of x comma y equal to x plus x small x plus y minus 10. Now, let us define capital F of x. You do know that capital F of x is just this small f of x plus lambda times g f of x, right? So, small f of x comma y plus L times g x comma y. Now, the first step in finding out the solution is this. Differentiate to obtain fx and fy, right? So we define an fx as diff. Now what this diff function basically does is it partially differentiates. Let's say that you do diff f comma x. Basically what it means is you're differentiating capital F with respect to x. Similarly, fy, define fy as diff f comma y. Basically what this means is you're partially differentiating capital F with respect to y. Now, recall that I said that we need to obtain a relation between fx fy. Basically, we do not need to do this here. We can just write s equal to solve. Now, what the solve function does is you give it a few variables, a few relations, and it basically gives you the common answers itself. So we're taking g, the constraint first, fx, fy, because the constraint fx and fy is the things we need to find a relation between, which we'll later implement to find the values of x and y, right? Now, real. Uh, real. Basically, what this real does is it assigns basically it gives you only the real solutions to this equation. It does not go after any imaginary solutions and to basically affirming that. So now we have our solutions. Now S will be a set of this type. Let's say 1 and 2 are the solutions. So S will be of 1 and 2. Now S will also have a x value and a y value. So x 1 comma 1x comma 2y, let's say. So basically there will be a x address and a y address for which we have to look. We can write this as STPTS, stationary points, as in the bracket s dot x comma s dot y, which means the x and y solutions of S, and S is that solve function. We know that already. Stationary points. Now, stationary points need to be double, need to be precise. So we'll use double precision on stationary points. Okay. Now, let us find the function of value at these points, because we are after all trying to optimize small f of x comma y. So function value equal to f of s dot x comma s dot y, and function value will also be in double precision. Okay, now this uh, stationary points, which will print the stationary points, and this function value. Okay, let's see if this works. Yeah, so this 5 is the value of x and y, and this 50 is the value of function. We can uh, also write display the stationary points are, I mean, if you want to, basically you do understand that this is what it is, right? But still, yeah, it will throw too many input arguments. Up to you if you want to do this. You instead, what you can do to get it is this: the stationary points are. Yeah, now close this, and then this the function value at that point is. Yeah. See, the stationary points are 5 comma 5. The function value at that point is 50. Now, I understand that this is not the part where most people have problems. The problem start where it always do, at the plotting. Now, for plotting, let's take a capital X. Note that this capital X is not the same as this X or any other X in the entire code, because capital X and small x have different addresses and are different variables within MATLAB. So let's say capital X as linspace. Now, I did explain this before, but linspace is a discretized point. Let's say that we have a range of values, right? Like let's say 1 comma 20, 1 comma 2. Now we know that on a number line there are infinite amount of points, because you can keep dividing 1 and 2 between the number lines, but there are infinite number of points between 1 and 2 on a number line. So let's say we'll take linspace 1 to 200. Basically what this means is that on a number line it will take 200 points from 1 to 2. This will include 1.0.5, 1 plus 0, and 1.0, 1.1, 1.15, like that. It will take 200 discretized points equally divided. Now, why do we need linspace here? Because the plot and surf function, like the plot function that we are going to use and the surf function, these cannot take actual functional values. They do not know where these functions are being defined. We need to define them on a plane, on a 2D or 3D axis. So min is, and I'll explain you what this min is. This min s dot x means that the minimum value of s dot x, like whatever s dot x we'll get, like the lowest possible value of s dot x possible for this s equal to solve to be valid will be taken. Now max s dot x. This means that the maximum value possible plus 3. Like we are just taking for precision 3 points here and there in case they aren't equal, because then the graph might be messed up. Now, what this basically means is we're taking the minimum possible value of x and the maximum possible value of x such that the s solve function is still defined, and we're taking say 20 points in between. Also double, because the data type for graphing these things is double. Now y, similarly, linspace min s dot x s dot y minus 3, max s dot y plus 3 and 20. Same thing, we are taking 20 points. We're taking 20 points in the y-axis now instead of the x, and y equal to double y. Okay. Now, after we have taken x and y, we need to define them as a mesh grid. Why? This is due to the fact that uh, yeah. Now we are defining x and y as a mesh grid. What a mesh grid means basically is that x and y is defined as a mesh grid containing these points for all x and y. Now, why we need this is because x and y are not is not defined as a 3D function by itself. We need to define it as a 3D function if we want to make a surface plot of it. Basically, what the surface plot does is it creates a 3D graph. You'll understand this further. X, Y, mesh grid X, Y. Okay, so let's take a new function z equal to f of capital X comma capital Y. This means that z we are defining as the initial function, but instead of x comma y, it's now linspace and mesh grid, and z equal to double z. You'll understand what I mean in just a few seconds. Now, surf x comma y comma z. Right. Run. Yeah, basically now what we have is three-dimensional plot of the function in x, y, and z planes. This is not over yet though. Hold on. Now, first of all, we must define x-axis, y-axis, and z-axis. Otherwise, the graph wouldn't make much of sense. You won't understand which planes are going where. So, x label, x-axis, y label, y-axis, and z label, z-axis. These are the three axes which we have defined. Run. Yeah, z-axis, y-axis, and x-axis. Now we know where the axes are. Now, after this, we still need to point out the constraint in the function. Like, we need to show where the constraint is. So, for this, what we do is we do gv equal to f implicit. Now, what this f implicit function does is it creates an implicit function and graphs it over the normal range of minus 5 comma 5. Now, instead of graphing it over the normal range, we are going to take an f implicit, we are going to extract the x and y values from it, and we are going to plot it we are going to overlay it over our original graph. And yeah, g. Like what this g says basically is that g is the function for which we are defining f implicit, and slash b. Yeah, this is the graph attribute. This b means blue, basically, and x. Now, hold on. Remember, we need to do two hold ons on this, and they must be at the perfect location, otherwise the graph will be messed up. Now, xv equal to get. Basically, what it does is it removes the any like GV's f implicit g with the color blue, right? So g contains both x and y values. Now, this using this get GV and x data, what we can do is we can extract the x values from the GV, from the implicit function. Now, yv equal to get GV comma y data. So now we have the x and y values, and do not double them. This will cause a problem. If you double them, it will cause a problem. And let us define a new function fv equal to f xv comma yv, and double this fv. Okay. Now plot 3, because we are plotting the curve in 3 dimensions, xv, yv, f. Also, the order of this is important, otherwise the graph will be messed up. Fv. Basically, what this last thing means is that there will be a straight line which will be red in color. Now let's run this. Hope everything goes fine. Yeah, beautiful. So this is the function of the graph that this is the graph of the functions that we have gotten. This doesn't make a lot of sense right now. So let's put up a legend here. Legend f of x. And when making legends, you don't actually have to use a lot of things. You just label this f of x. Now we know that the blue line is two-dimensional 2D constraint, and the uh, 3D line that we got from plot 3 is red in color. So we can write that as 3D constraint. Now run. So command menu now. Yeah, so basically we can now map the f of x 2D and 3D constraints. Yeah. So and this is not completed, by the way. We will be looking at some examples, but before that, we need to look at a look at a three-dimensional problem. Generally, I'm not going to change much of the syntax for you here. Basically, what we are going to do is we are going to x, y, and z. And remember, there's no plotting for these three-dimensional functions. Okay, so z cube, let's say, it doesn't really matter. Z and f of x, y, z again x, y, z, u of x, y, z. Now there is an fx, fy. You will need to define an fz equal to diff f comma z, differentiating that with respect to z, and s equal to solve g fx, fy, fz uh, real true. And the stationary points will still be the same thing. Stationary points will be s dot x comma s dot y, and stationary points will be double precision, which is obvious. Now function value will still be function f of s f of s dot x comma s, okay, s dot y comma s dot z. This will be the function value, and function value will also be double precision. And you can then display them. Well, I think it's time we move on to other examples. Most examples are of 2D because plotting is a much more important part. Let's look at some examples. First one, f of x comma y is xy subject to constraint x square plus y square minus 1. So the original function that needs to be optimized is x star y, and the constraint given here is g of x comma y is x square plus y square minus 1. X square plus y square minus 1. Uh, if our code is working for this, then it will work for anything else. Also, close the figure. Before you run the code, close the figure, otherwise they will overlap. Okay. The stationary points are these, and the function values are these. At these points, remember that these are mirroring, like minus 0.7071 minus 0.7071 gives the value of 0.5, like that. And the function graph is this. Here you will notice that the constraint is circular. It's not it's not how it usually is. It's not a line. Now let's take another problem. Let's take exercise number 2 and exercise number 3, and then we'll end this session. Now here also remember that for Lagrange multiplier, the f of x comma y is usually given. It won't have any constant attached to it, but the g of x comma y will have a constant attached to it. Here f of x comma y is x square into y square, and g of x comma y is 2 into x plus 4 into y minus 40 equal to 0. Okay, so f of x comma y is x square dot y square. Also, this dot is important because otherwise it might think that they are cascading, like x to the power 2, 2 into y to the power 2, and we don't want that to happen. And 2x plus 4y minus 40. 2x, also remember the star. That's where a lot of the errors happen. Okay, let's run. Yeah, the stationary points are this. The function value is 2500. Uh, you can have a look at the stationary point 0, 10, 20, 0, 10, 5. Function value 0, 0, 2500. 2500 is what we need, which occurs at 10, 5. And this will be the function plot that you'll get. Okay. Now let's take another problem, and this is actually the first problem I discussed in today's session. Now it's saying the dimension of a rectangular box with largest possible volume. Now it's saying largest possible volume. This implies that the volume is the function that we have to maximize. Now let's assume that the cube is well cubical with length, breadth, and height. Now we define the length as x, breadth as y, height as z, and also says that it is open on top, and it is to be constructed with 162 square inches of cardboard. Now we know that the closed surface area of a cube of a rectangle is 2xy plus 2yz plus 2zx. Now we know that it is to be open at the top, so remove any one dimension, x, y, yz, zx, doesn't matter. So that will give us our constraint. Now what our constraint basically is 2 x star y plus 2 star y star z plus 2 star z star x minus 162. Yeah. This will be our constraint. Now the function to be optimized. Now recall the volume of a rectangular box is x star y star z. So this is the function that we need to optimize. X star y star z. I guess that's it. Now also close the figure. Very important. Run. Yeah, almost forgot. Y z, and this is a problem in 3 dimensions, right? So f of x comma y comma z, g of x comma y comma z, and the capital F of x comma y comma z, small f of x comma y comma z, g of x comma y comma z. Let's get rid of all of this plotting part because we don't need it anymore. This is in 3 dimensions. Now let's define fz as def f comma z, fy fz, here to s dot x, s dot y, s dot z, y, s dot z. Run. Oh yeah, almost forgot this. Stationary points, function value, and disk. The stationary points occur at stationary points, and thus the function value at points are now. Yeah, the stationary points occur at these points, and the function value is this. So I guess that's it. We successfully discussed how to use Lagrange multiplier to solve multivariable functions with a constraint. We also went through a few iterations, a few different codes, and we saw how we can use the Lagrange multiplier and how we can plot it to get the exact get the idea of what what these functions look like. Basically, we looked at these examples, third and second. Now, the second example doesn't really make that much sense from a from a realistic point of view. It makes sense from a data point of view, but the third example is very illustrative. You basically get to understand how to optimize a function. Here the function was x comma y, x star y star z, and with respect to the amount of material. Basically this is how real life problems work. So I guess that's it. Thank you.